Okay, so this is lecture 6, and what we're going to do is just start with a little warm-up problem. So Tim has thrown something on the board, and the in-class students have been working it. So what I'm going to do is just kind of hop over near him and copy it. And again, the main purpose of this is to sort of arm you with a couple different ways of solving a problem. And so Tim, you're going to kind of go through the step-by-step way, and then after he gets that dialed in, I'll go in with sort of a more spreadsheet, nail it in one shot type of way. So I'm just going to move across the room. And Tim, I think we can probably hear your audio okay. Actually, no, I'm going to have to move right over here so I can see you. Yeah, this will work.
And you want to read that out loud to them so that they can see it?
Yeah,
we can do as well.
Okay, so what we're looking at on the board, it says the average light bulb is 10% efficient, and by efficient that means that 10% of the energy goes into making photons come out of it, and 90% go into making heat of something that you cannot see. It says if you use 5 60-watt light bulbs for 8 hours per day, how much energy is wasted per year, or how much energy is turned into heat per year? And then the next question is, next part of the question, if electricity costs 10 cents per kilowatt hour, how much does this wasted energy cost each year, or how much are you paying to heat your house, whether it needs it or not? So.
All right, so we take a look at this problem, this typical word problem. Is there any information that you see in there that's not useful? Is there anything there that we can just cross out right off the bat?
Not really.
No, not really. Unlike the other question last week, you kind of need everything there. So what do we know, looking at this question, what are the information things that we know out of this? We know 10% efficiency, right?
So I just wrote down the efficiency of the bulb is 10%, so that's our first bit of information.
Okay, keep going. We know there's five light bulbs, right? Each one is 60 watts. And we run them for 8 hours a day. So now, is that pretty much all I'm not gonna worry about question number 2 yet.
To start with, yeah.
Yeah. So this is part A, where we're just looking at energy. So we've got an efficiency of 10%, just so you can interpret my scribbles here. We've got the number of bulbs equals 5. We've got the power per bulb at 60 watts. And our run time is 8 hours. So that's kind of the 4 chunks of information that we pulled out of the word problem so far. Yep.
All right. So now where would you guys start with this
Multiply
equation?
5 times 60.
5 times 60, right? We have 5 light bulbs at 60 watts each. Gives us,
300 watts.
so 300 watts.
I guess what I don't know is that watts per hour? The 60 watts is that per hour?
We haven't thrown the hour into the equation yet. We are just at watts.
Okay.
And they're running, when we turn them all on, that's 300 watts going out. So we haven't added in the time factor yet. So now we can get this and figure out that, actually, where do I want to go with this? You guys tell me.
Multiply 300 by 8 hours, so you need 2,400 watt hours.
So
you convert that into kilowatt hours, you get
So that's going to be
4 kilowatt hours.
times 8 hours. Gives me 2,400 watt hours. So I got my watts and my hours now. That's where that's where your time factor comes into it. So
it is 300 watts per hour then?
I'll address that question
Yeah,
in a little
we'll-
bit. I'll address
okay.
that. I'll address that in a little bit.
Don't you want to do that for the year? So times
Yeah.
365 then?
well, eventually, yes. That's where I'm going next.
Way off.
Convert to kilowatt hours though first, right? Because that's what we're using up here. So
Add 3 zeros, right?
Take away
take away 3 zeros.
2 places.
So I'm going to over
Oh,
3
that's
places.
where I went wrong.
Gives me 2.4
Kilowatt.
kilowatt hours per day. So now I know how much is a day, how am I going to figure out for a year?
Multiply times 365.
Multiply times 365, right?
876.
So I multiply that out, 365 days, my days cancel out, and I'm gonna be left with that, how many kilowatt hours per year? Which one was that number, I'm sorry?
876
876
kilowatt hours per year.
kilowatt hours per year. All right,
Or multiply that by 0.9.
okay? Because that's gonna give me my, what?
Your dead space, your negative efficiency. or
That's the
what's
wasted-
not your heat, what is not efficient.
Okay, so what doesn't come out is light, what comes out is heat. So we multiply that times 0.9,
788.4 kilowatt hours.
788.4
Kilowatt hours per year that are not efficient or come off as heat, not light.
year wasted, okay?
What's the number one more time for the total wasted?
788.4.
What did I do wrong? Oh, nothing, 788.4, okay, thank you, yeah. 788.4, and that's kilowatt hours per year, right?
Yes,
Yeah, okay. So that's the answer to part A.
yes. Okay, so how would I go about finding part B?
Multiply that number by 0.1.
Okay? So 788.4. Right, yeah. Kilowatt hours per year. So
$78.94.
24 cents. Is that what everybody came up with, or something pretty close to that?
No.
As we did it step by step through there, do you see where you missed?
Oh, yeah,
Any
yeah,
advantage?
I followed it right on down. I just didn't think to multiply times the negative space and or lost heat to get that answer. I
Okay.
just used the direct 10 cents.
Right, and you could do that either way. You could use the 10% efficiency, you could multiply that number, that 876 kilowatt hours per year times 0.1. And then from there, you know, your 876 total minus that 10% that goes out as light, the other whatever
90%
remains.
is your answer.
90%, yes.
Okay, okay.
So you can do it either way. This just shorts us, takes away a step by doing the 0.9.
Okay.
Does that make sense to everybody? Pretty simple, but it's the idea of taking a word problem and working it into a math problem.
Yeah. Okay, I'm just going to review it really quickly here since I'm sitting close to the computer, and I just want to make sure that if there's somebody online listening, that they could hear everything. 'Cause sometimes the voice from across the room doesn't pick up all that great. So the problem was the average light bulb is 10% efficient. If you use 5 60-watt light bulbs for 8 hours per day, how much energy is wasted every year? If electricity costs 10 cents per kilowatt hour, how much does this wasted energy cost per year? So I wrote down, and the problem is written very efficiently in that there's no information in the problem that we don't need. So the efficiency of the bulbs is 10%, and I've also written that out just as in decimal form, because that's typically when you're punching things in your calculator, typing in percentages, I've always found is a little confusing. The number of bulbs is 5, and you'll notice that both in the case of efficiency and in the case of the numbers, there are no units. These are unit lists. They are dimensionless. I've also written down the power of each bulb is 60 watts, and we know that we're running for 8 hours. So obviously, there's your units of power, and there's your units of time. Now, I want to take this opportunity to reiterate the fundamental equation of NRGY 101. And that equation is energy equals power times time, or power equals energy divided by time. And I did hear this from, I heard this from one student. I'm going to try to do a little kinesthetic learning, because I know that's kind of a, a buzzword. Well, no, I heard kinesthetic learning for the first time, gosh, I don't know, 4 or 5 years ago, and I think it's an actual, it's a real thing. So it could be that some of you in this class are kinesthetic learners, and in fact, I think a lot of men are. So let's look at the difference between energy and power. So right now, I've got this book sitting at some height in the classroom. It has some energy. How do I know that? Well, if I drop it, it just gave up its energy, right? Now, I just let gravity kind of have its way with it, right? But what about this? It got to the ground faster. Why is that? I put some energy into it, and so that was a more powerful reaction. Now, the book, at the start, and let's just say this, book has a certain amount of mass, and we'll get into this later in chapter 4, 5, and 6. It's got mass, it's got height, and it's got gravity going for it. Those three things give it energy. When it's laying on the ground, it has that much less energy. We can quantify that later, but for now, so that's energy. But if I shove it to the ground more quickly, it lost that energy more quickly because it was a more powerful action. It took place over a shorter amount of time, right? So that time, I just reduced the amount of time. So if you remember from algebra, when the denominator gets smaller, the thing on the left-hand side gets bigger. So just another analogy for you, for energy and time. I hear this all the time. It's like, well, how many watts per hour was that? Well, that's a question that it's not a valid question, and I'll show you why. So another example is, if I'm standing here now, I'm not actually gaining any energy by moving over here, but it took some energy to move myself, obviously, my legs and muscles and all that. So the best way to think about energy is moving from here to here. It took some energy to do that. And energy is like distance. Just like the book fell vertically, I just moved horizontally. Think of that in terms of energy. Think of energy like distance. Now, how would I do that same action with more power? What would I do? Just go faster. I had to be more powerful. So think of power like velocity. So asking the question, how many watts per hour was it, would be a little bit like asking how many miles per hour was that. You would never say I went 60 miles per hour. You might say, oh, I went 60 miles per hour for an hour. I went 60.
Math tells you that that's exactly what it is.
Yeah, exactly. I went 60 miles per hour, that's my P. For 1 hour, that's my time. When I multiply my power times my time, I get energy. When I multiply my velocity times my time, I get distance. So hopefully that drives home the distinction between what energy is and what power is. They're two fundamentally different things. They're as fundamentally different as distance and velocity. So 60 miles is very different from 60 miles per hour. Is that
No.
Not helping?
I'm more lost than I was 10 minutes ago, but it's okay.
Well, so the 60 watt bulb is it's a 60 horsepower car. And it's, you know, running it at 60 horsepower. Or at 60 miles per hour. That's how fast it's going. It's going at 60 watts. If you want to know how much energy it is, you can't just convert from energy to power. You have to say, well, how long was that 60 watt bulb running? Well, 8 hours. You multiply power, which is measured in watts, by time, which is measured in seconds, and you get energy, which is measured in kilowatt hours or joules or what have you.
I'm still at a loss, because if that was 60 watts a minute, your entire equation is completely different.
It's not 60 watts a minute.
Well, I mean, I realize that.
Yeah, there's no such thing as 60 watts a minute. It's just plain up 60 watts. Just like you never say I'm going 60 miles per hour.
You wanna write that as horsepower instead of watts? You can do that.
By changing it is just confusing me even more.
60 watts a minute. How do I do this?
So it's like, it's almost like a.
Well, if there's 5 60 watt bulbs, which goes to 300 times 8,
Electricity,
which
say
is 2400, that means it uses 60 watts per hour.
Almost like a speedometer for how fast electricity
Yeah.
is flowing.
Yeah, you can think of the watts as a speedometer, for sure, yeah. I'm sorry, what was your question one more time, Rand?
Oh, it's okay.
Yeah.
I'm just lost, it's all right.
Yeah.
Can you just, like, can you do minutes and then the unit would just be a watt minute? Or
Sure.
if you did a year, then it'd be a watt year?
Sure.
Or a decade, it'd be a
It
watt?
could, yeah.
Yeah, because we ended up with watt hours, and we wanted to convert to kilowatt hours so we could get, for part B of the question.
Well, let's think of it this way. Let's think of it in terms of money. Let's just say you're making $10 an hour. Would you say I'm making $10 an hour per hour?
No, but there's no hour relation there.
Oh, there is. A watt is a joule per second. Just like a dollar, or a joule is a dollar. A joule is a dollar.
That makes more sense.
Yeah, there you go. So you can think of it in terms of money, and you wouldn't say I'm making, so the 60 watts means I'm making $60 an hour. Or in this case, 60 joules per second. That's how fast I'm burning through that energy, just like how fast I'm making money. So you would never say I'm making $10 per hour. You would say, oh, I'm making $10 per hour, and I work for 10 hours, so I got $100. Yeah.
And don't worry about, dimensions of these are difficult to represent.
Yeah.
The more you go, the
Yeah.
more sensitive. it will be.
Yeah. And we'll hit this a bunch more. It's not, we'll keep working on it, so. Thanks for asking that question. All right,
So
so.
Brad's getting set up over there. Can we convert watts to horsepower? That's a 60 watt bulb. Do we know how many horsepower that bulb is?
Good question.
Well, 746 watts equals 1 horsepower. So how could we figure that out? Mathematically, there's.
Divide.
Yeah, if we divide it 60 by 0.746, that'll tell us how many horsepower it is, right? Should be a little less than a 10th horsepower.
Yeah, that's and the exact numbers in table A7, page 628, yeah.
Oh, it isn't?
Yeah, it's in fact, it's the very last conversion in the whole book.
Nice. Now you know.
Yeah. Okay, so let me, so Tim ran through it in one way, and I think what we've found here is it's usually good to go through the problem in a couple different ways. Everyone's got their kind of favorite way to solve it, comfort zone, what have you. So let me just run through it in a way that's comfortable to me, and which will sort of allow you, like we said before, a way of not necessarily having to go back and say, oh gosh, where did I make my mistake? In fact, earlier today in class, I was moving through a problem this way, which is usually the first way you would go through it. I made all kinds of errors. I had to go back, erase, and then come back down. So let's, I'm just gonna run it like so. So, if I've got, so I know what I'm looking for in the end is the amount of energy. I know that I'm looking for some total amount of energy. And I know that the more bulbs that I use, so N bulbs, so I'm just going to say energy equals. So I'm going to get bulbs in the numerator. And I know that the more powerful they are, the more energy I'm going to use. So I'm going to put P bulbs up here. Right, more power is going to take more energy, and I also know that the more time run is going to be more, and then the next thing I'm going to write. This might be a little bit tricky, but since we're looking for the amount of heat, I'm just going to write the number 1 minus the efficiency, and that symbol that I just wrote there is the letter eta. It's the same as H in your keyboard. So in this case, in the denominator, everything is just 1. It's just kind of a straight up deal. So I've written it algebraically. Now let's put the numbers in and the units, and we'll be in good shape. So what I'm looking at here is the number of bulbs is 5, and there's just a 1 in the denominator. The power of the bulbs is 60 watts, and again there's just a 1 in the denominator. The time run is 8 hours, and now I'm going to have to start paying attention to units. It's 8 hours per day, and I'm going to have to complete this with time by saying I've got 365 days per year. And then finally, I'm just going to multiply it by 1 minus 0.1. That's the efficiency. Now, from here, I know I've also, oh, and there's one more thing I think I'm going to have to do. I've got this thing in watt hours per year. So the next thing I'm going to do is multiply. I know I need kilowatt hours. So if I put 1,000 watts down here, I'm going to have 1 kilowatt up here. So that last little thing I did was just a change of units. Going back to our powers of 10, we know that 1K equals 1,000. So I was able to, stack that entire work problem into one line. All that information that we went through should be contained in this one thing. All the numbers, all the units, and now it's just a matter of accounting at this point. It just comes down to accounting and a little bit of arithmetic. So let me first scratch through the watts. I will scratch through the days. And what I'm left with are kilowatt hours per year, which is exactly what the question asked for. How many kilowatt hours per year get turned into heat? So I've taken care of the units. Now it's just a matter of arithmetic. So 5 times 60 times 8 times 365 times 0.9 divided by 1,000. Is that the right answer? Is that what we got, 78?
But 0.9 isn't on your scale, 0.1 is.
1 minus 0.1 is equal to 0.9.
Okay,
Yeah,
okay.
yeah. Yeah, 1 minus 0.1 is the 0.9. That's why I entered the 0.9. So anyway, that's just another way of doing it. And then obviously multiply that by a dime and you're going to get $78.08. So couple different ways to knock that problem out. And again, I encourage everybody to solve it both ways. I mean, it might seem kind of boring at first, but I'll guarantee you, anytime you're in a technical position, engineering discipline, these numbers are not going to get out the door until they've been double-checked, triple-checked. So just do yourself a favor and double-check them, triple-check them with a couple different methods. All right. So I'll just take a little pause here, and then we'll pick up with the rest of the course. And what I would like to do today is, so I feel like we've spent some time on problem sets, quantitative work. We'll look at the summary a little bit, and then we'll get back into the textbook. So we're kind of hitting on all three things. Oh, and I guess just for the sake of completeness, I want to re-emphasize again that in this course there are three fundamental things that are required for your grade. It's doing your exams, doing your summaries, and doing your problem sets. I also want to see you participating in all that, and as long as you are, that's fine. And there's going to be one of those three things due per week, either an exam or a problem set or a summary. They are due at the end of lecture on Thursday, and they are late at the beginning of lecture on Tuesday. So I just want to make that clear again, because I had another student email me, ask when things are due. He also mentioned the fact that there's a little bit of discrepancy between exactly what's in the Moodle shell and what's on the syllabus. We might be introducing things in the Moodle shell a few weeks prior to when they're due, but the syllabus itself, and I will hop right back into the syllabus again. The syllabus is the master document, if you will. So let me just get back into the 101 syllabus. So here it is one more time, right at the very top of the page and at the bottom. So we are at the end of week 3. Your summary 1 is due, what time is it? In 40 minutes. And it will be late on Tuesday at whatever time we start, 1 o'clock. Yeah, 1300 on Tuesday. So you've got Friday, Saturday, Sunday, Monday. I mean, you got almost a 5-day window to submit that summary 1. So again, that's so things are due at the end of class on Thursday, and they're late at the beginning of class on Tuesday. Okay. Just want to reiterate that one more time.
We should say, just to clarify that.
Yeah.
The gate opens.
Yeah.
The gate opens,
The
okay.
gate opens at 1500 on Thursday
Right.
afternoon. That means you can start submitting them.
Okay,
The gate closes at 1300 on Tuesday.
There we
So
go.
anytime that gate's open, you can put it in there.
There you go.
If the gate's closed, you're not getting in
Yeah.
it, so.
Right, there we go. And we will accept late work, but there's a 10% penalty for each day that it's late, so I think that's fair. All right, and we reviewed exam 1 last week, right? I mean, I think we did that, oh, sorry, on Tuesday, yeah, so last time we reviewed exam 1. There were a few tricky problems. There's always going to be a tricky problem. If you're not getting tricky problems on an exam, we're not testing you properly, and part of the point is just to make you think it through and not just read the book and spit it back at us. So, all right, it's a good time to pause.